Hi everyone, I'm Yuliang from Harvard University. Today I'm going to introduce our work, DETER, which enables deterministic TCP replay. And it greatly helps diagnosing TCP-related performance problems. This is a joint work between Harvard, MIT, and the Alibaba group. TCP performance diagnosis is very important today because applications are getting more distributed. So they increasingly rely on the TCP to achieve high network performance. And also the tail latency is very impactful because a single long latency can slow down the entire task, which often have thousands of requests. So when a problem happens, we need an effective diagnosis tool for TCP in large-scale production network. So why diagnosing TCP is hard? I ask this because this is what I learned in the textbook. The sender just has a simple state machine, and the receiver just an X. But after I get hands on the real TCP stack, I find it's way more complex than I expected. You don't need to read it because it's too complex. There are lots of components, and they can interact with each other in various unexpected ways. For example, sometimes the receive window manager can mislead the loss recovery at the sender and stop the fast recovery. Sometimes the sender window manager may mislead the attack mitigation at the receiver side, so the receiver ignores the packet and causes no response. All these problems stem from the complexity of TCP. And there are two factors that make TCP even more complex. The first is that the behavior of different components are not static, but affected by lots of parameters that are very hard to tune. Second, TCP is under continuous error-prone development. In just 2 months of 2018, people find 16 bugs in Linux TCP stack. So how do we diagnose TCP today? It's a very popular tool and everyone uses it. It's called TCP dump. It's a groundbreaking tool, but only 30 years ago. Although it's still the gold standard of TCP diagnosis, it is not scalable anymore because the scale and the speed of the network has both increased by more than 10,000 times. So turning on TCP dump in production is too much overhead. In fact, all existing tools face the tension between getting more details for diagnosis and keeping the overhead low. They either record lots of details but incur high overhead, or they keep the overhead low but miss lots of details. They cannot achieve both because what they record in the runtime is all we have for diagnosis. In other words, they are all one-shot solutions. It seems very hard to break this tension unless we can get more information from the data we record. And this is what DETER achieves by introducing replay. In the runtime, we just turn on the lightweight recorder, and in the replay, we can replay every detail. Here's an overview of DETER. During runtime, we turn on the lightweight recorder all the time. And when the user reports a problem, such as a long latency, he can get related records from both the sender and the receiver and launch the replay. He can turn on any detailed diagnosis tools, such as he can capture packets. He can even trace the execution of TCP. And he can even replay multiple times to diagnose the problem iteratively. So these two are the key features of DETER. The intuition for being lightweight is very simple. If we record all the socket calls and re-inject them, the TCP automatically regenerates all the packets. But simply record and replay the socket calls alone cannot achieve deterministic replay because there are lots of non-deterministic interactions with many parties, including the switches, other connections, and also the kernel. Our key contribution is to identify the minimum set of data that enables deterministic replay. This requires solving two challenges. The first is network-wide, which involves the non-deterministic interactions across the switches and TCP connections in the network. And the second is on host, which involves the non-determinism in the kernel. We now introduce the first challenge, which is the most challenging part because it involves a butterfly effect. The butterfly effect is caused by the closed loop between the TCP and the switches that amplifies any small noises. Let's see an example. We record socket calls during the runtime and re-inject the same socket calls in the replay. In the runtime, the orange packet arrives slightly earlier than the blue packet, so the blue packet gets dropped. In the replay, the sending time of packet may have microsecond level variation due to reasons like clock drift, context switching, kernel scheduling, or CPU's cache state. So these two packets may arrive in a different order at the switch and cause the switch to drop a different packet. This is called a switch action variation. This will in turn cause TCP behavior variation because TCP change congestion window according to packet drops. Such TCP behavior variation cause more switch action variations. In the runtime, the orange flow sends more packets because it increases the window. And the green flow drops a packet. Green flow share a queue with it and drop a packet. But in the replay, the orange flow sends much fewer packets, so the green flow has no drops. This causes more TCP behavior variations. And in a similar way, it will propagate to more and more flows in the whole network. We call this a butterfly effect because it dramatically amplifies the small sending time variation. To understand the impact of butterfly effect, we perform a very simple experiment. We try to replay a long latency problem in a small testbed with 3 flows by issuing the same set of socket calls as runtime. And we replay 100 times, but none of them reproduce the same problem. One natural question to ask is whether reducing the sending time variation can help. So we perform a simple experiment in simulation to control the level of sending time variation from 0 to 1,000 nanoseconds. And we count how many times we can reproduce the same problem under different level of sending time variations. Unfortunately, even 1 nanosecond variation still causes the butterfly effect. So reducing sending time variation cannot eliminate the butterfly effect. This means we must break the loop. So since we cannot avoid the switch action variation, our goal is to control the packets into TCP to break the closed loop, and thus eliminate the butterfly effect. This means we need to record and replay the packets before the packets enter in the TCP. There are many literatures on replaying the kernel, and they can also replay the TCP. But their overhead is very high because they require to record every packet, so we cannot directly use them. So let's step back. We find that most of the packets go through the network without any changes. So in the replay, we can just let the other side generate them. All we need to take care of are the packet drops and the ECN marks, and sometimes reordering. These are the mutations to the packet stream from the other side to this side. So we can make the recording very lightweight by just recording these mutations to the packet stream. And in the replay, we re-inject the same mutations to the packet stream. This approach has very low overhead because the number of packet drops is very small compared to the total packets because the drop rate is very low in data center. And ECN just take 1 bit per packet, and the reordering is very rare. Also, the replay of each TCP connection is independent. This is because different connections interact with each other via the packet drops and the ECN, which we already replayed. So we don't need other connections in the replay. For the same reason, we also don't need a switch in the replay because we already re-inject the drops and ECN. And in this way, we get rid of the butterfly effect. These two features means that the replay is very resource efficient because we don't need a whole network of hosts and switches, but just 2 hosts. Let's see how it works. We use drop as an example. Reordering is very similar, and ECN is easy to record. We detect drops using the IP ID field because it is consecutive within each connection. Normally, we don't record anything. Once a packet is dropped, we don't see it, but later packet help us detect it because there is a gap. In this way, we only do the recording on the end host, not on the switches. And in the replay, most of the packets just get through. And we only drop the packet that should be dropped. This solves the butterfly effect. The second challenge is the non-determinism within the kernel. Let's zoom into the TCP stack. We have already recorded the socket calls and the mutations, so we already get a correct input into TCP. And they are fed into TCP via the corresponding handler functions. The first non-determinism is other handler functions. For example, the OS timer may call the timeout handler. We need to record them, and in the replay, we call these handler functions accordingly. These handler functions are called by different threads. So this leads to the second non-determinism, which is the thread scheduling. Normally, risk conditions are very expensive to record and replay. But TCP use on one single lock to prevent risk conditions. So we just need to record the order of lock acquisition by different threads using our customized lock function. And in the replay, the function will enforce the order of locks. The third type of non-determinism is that TCP sometimes read variables not only updated by TCP, but also updated by outside of TCP, such as GFIS. So we use a customized read function to record the value, and in the replay, we re-inject the same value as recorded. All these recordings are very lightweight because other handler function calls are very few, and there are often tens of consecutive logs by the same thread. So we can compress them a lot by recording the number of consecutive logs from one thread. And we use various techniques to reduce overhead of recording kernel variables based on the characteristic of each variable. For example, the GFI changes its value very infrequently, so we just record when it returns a new value. Our prototype in Linux 4.4 shows that the recording is very lightweight. The storage overhead is just 2 to 3% compared to compressed packet header traces. And the CPU overhead is always lower than 1.49%. So it doesn't affect the TCP performance. All data are recorded on the end host. And we just need to change a total of 139 lines in the Linux TCP. We will soon open source our project, and you are all welcome to use it. Let me give you an example to show the benefit of DETER. We perform a simple congestion experiment in a testbed with 2 senders and 1 receiver. Each sender sends 1 long flow, and one of the sender also sends a short flow. The short flow experienced 49 millisecond delay, which is way higher than expected. In contrast, the retransmission timeout is only 16 milliseconds. We first try to use the counters to understand the problem. It shows there are 2 RTO, but 2 times 16 is still less than 49. So we use DETER to replay and capture the packet trace. We see there are packet drops, so the sender has to retransmit after an RTO. The receiver does not respond, so the sender has to retransmit again, and then the connection resumes. The first RTO is 16 milliseconds. The second one is 32 milliseconds because they are consecutive, so it experiences exponential backoff. But this raises another question, why the receiver does not send an ACK for the first retransmission. So we replay again and monitor the function call graph at the receiver side. We see that the receiver enters the delayed ACK function, which means the receiver decides to delay the ACK, which explains the problem. In this example, the counters only shows that there are 2 RTOs. With DETER, we can capture the packet trace and find the exponential backoff. Some TCP experts may also guess this, but it's not accurate, and also it's still not enough to understand the root cause. With DETER, we can go deeper and find the root cause. And even normal developer can diagnose problem very easily. Now we show some running example in production networks. We perform a case study that sorted 200 gigabytes data on 20 servers on EC2 with a total of 6.2K connections. We replay and collect trace for the problematic flows, and they are all accurate. One flow is of particular interest because we see it has multiple delayed ACK timeouts. The sender often sends a burst of packet, but the receiver does not respond until 40 milliseconds later, and send 1 single ACK for the whole burst. So we use DETER to replay and trace the related TCP state variables, and we find the receiver explicitly delayed the ACK because the receive buffer is shrinking. So this seemingly TCP problem is actually caused by the slow receiver. We also do the same analysis for all flows and get an overview of reasons for tail latencies of different flow sizes. We also perform a case study in an RPC application which run empirical data center traffic in the same cluster. And we also found one interesting problem where the fast retransmission happens after tens of duplicate ACKs. This is unexpected because usually it should happen after just 3 duplicate ACKs. So we use DETER to replay and trace the threshold for the duplicate ACKs. We find it increased from 3 to 45. And for the replay diagnosis, we find that it is because of the reordering happening in the past of the connection. Similarly, we get an overview of tail latency for different flow sizes. We also use DETER to diagnose many other problems, such as RTO caused by different reasons. And we also diagnose problems in the switch queues. We can do this because we have packet trace on all the hosts, so we can push all the packets into the network in a simulation that accurately models the switch data plane. We use this approach to detect a temporary black hole that is caused by the switch buffer sharing. Please refer to our paper for more details. In conclusion, we show that DETER is very effective in diagnosing TCP-related problems. its recorder is very lightweight, so we can run it continuously. And when problem happens, we can diagnose problems using very detailed tools in the replay. We solved the key challenge, butterfly effect, by recording and replay packet stream mutations to break the closed loop between TCP and switches. This concludes my talk. Thank you for listening.
All right, questions, Rodrigo.
Rodrigo from Brown. This is extremely cool work, really cool. One question I have is like, to do what you did, you need traces and complete access and both sides to be running pretty much the same version of the kernel and everything, right? At least to have instrumented. So what are your thoughts when you don't control one of the sides and you can only do this on one side? Or is there a way to standardize the collection such that a Linux talking to Windows could perhaps share these logs? It seems like an interesting challenge.
Yeah, this is a very good question. Yeah, so actually, our current system does require that both end of the connection has the DETER turned on. And this is most usually true in data center, either by the data center company internal users or the cloud users because they own their application. And it's true that if you cannot control the other side, then you cannot use it.
Is there an intermediate solution, or is there a future vision of how, like, thoughts on how this could work?
Yeah, actually, you can do this by if you only record one side, you can still achieve the replay for this side, but you need to record every incoming packet from the other side. That's the requirement. Yeah.
Thank you. So, did you record the arrival time of every single packet?
Arrival time? No, we don't need to record arrival time.
Then do you think the slight variations of queuing delay in switches will cause a butterfly effect? Because you are now recording the timing difference between packets, and if the arrival time is different in replay and in production, maybe the state in the state machine will have slight variations. So what's the case here?
Yeah, so that's actually a very good question. So you are concerning that if the packet arrives at a slightly different time, yes, the TCP may change its state based on the different time in a different way. And yes, so the TCP, think in this way, how does TCP know the time is different? It do it by checking the log, which is a kernel variable. And we already replay the accurate kernel variable reads. So it's always see the same time gap based on the read to the logs.
So you recorded the order of the log access or variable access versus the number of packets you're seeing. Is that correct? So sorry, let's talk offline. Yes, thanks.
Okay, thank you.
So I actually have a similar question to his, except even on the send side, if you're not recording the times, how some of the analysis you talked about inter-arrival times or about RTOs. I don't buy that your lock argument is not sufficient to get determinism on exact times. So what do you exactly mean by determinism? For example, you talked about this 49 millisecond gap. Can you really recreate that between two replays? What are you assuming? Are you assuming the same hardware? Are you assuming the same software? On multi-core processors, the kernel itself is preemptible. Are you assuming no preemption there? What do you have control on, and what does determinism mean in this case?
Yeah, that's a good question. So you are concerning if we don't control the packet timing,
you don't record the packet timing as far as I know for non-drop packets.
So here we accurately replay the execution of TCP stack code. So every events, every packet generated are always correct. And in our paper that we didn't mention here, we also sample a very small fraction of the timestamp and use the logic time between different packets to recreate the timestamp.
But on Linux, the TCP stack is itself affected by other things that are not in the network. So for example, other I/O activities affect timing for the TCP stack. So why is recording the TCP stack sufficient in your case?
So you are considering other interactions between TCP and the other part of the kernel?
Yeah, because TCP is a preemptible part of the kernel. So anytime you receive an I/O interrupt, for example, or I'm doing, or my kernel, or I have a page fault or anything else, you should see timing effects. Why are you not seeing any of those timing effects?
Yeah, because so in general, TCP is a software, right? The way to replace a software is first you control the input, then you control the thread scheduling that run the code, and also you control the internal read, the read to read off other outside of the software. And as long as we accurately replay these things, the software is accurately replayed.
I think we should stop that here and continue offline if necessary. Any other questions? All right, let's thank Yuliang again.